Hi everyone, in this video we're going to go through section 26.5 called Moments of Inertia. And in this section we deal with rotational motion. Moment of inertia kind of describes how much an object tends to resist rotation. And as far as topics go, this is another application to integrals. Ultimately, it will boil down to a formula. This one might be a little bit more of an abstract application. You may have seen it in a physics class in the past, or you may see it in the future. But it again, it deals with rotational motion, and ultimately it'll boil down to being able to set up the right formula, the right integral using the given formula. We'll start out with a hopefully straightforward example. To kind of begin introducing the formula. So we have our axis, let me get my pointer. We have our axis of rotation here, and we have three different masses that are different distances away from that axis of rotation, and we define the moment of inertia, I, capital I, as the sum of the masses times the distance squared. So m1 d1 squared plus m2 d2, d2 squared plus m3 d3 squared. And so that's kind of where the initial formula comes from. And so think about if we had, an infinite number of masses, or m different masses, all different distances away, we can make that formula as big, as lengthy as we want to. Now, if we said that all of those masses were actually the same distance away from the axis of rotation, we can kind of transform this formula, make it look a little bit different, and have m1 plus m2 plus m3 all times this capital R squared, where R represents that distance, all three of the masses being the same distance away from the center of rotation. And we give R a special unique name. R is called the radius of gyration. Radius of gyration. Okay, and it's just the distance that the masses are from the axis of rotation. They're all the same distance away from the axis of rotation. We'll start next with an example that doesn't involve any calculus, so that makes it a little bit better, where we have to find the moment of inertia and the radius of gyration for this array here. All right, and we'll do the moment of inertia first, and that formula that we were just given, that I just gave you on the previous slide, says to take each mass, so I'm looking at this mass here, and you multiply by the distance away, -2 in this case, squared, distance away from the center of rotation, or the axis of rotation, excuse me, and then you add a mass of 5 grams times 1 squared. That's this location right here. And then you add to that a mass of 4 grams times 4 squared. There's my object right there. So my moment of inertia is equal to 3 times 4 plus 5 plus 4 times 16. And that gives you a moment of inertia of 81. And then the units are grams centimeters squared. Grams centimeters squared. All right, so that's the first part, find the moment of inertia. Then the radius of gyration. The radius of gyration we find by taking the moment of inertia and dividing by the mass, and that would be actually I'll write it out as the sum of the masses, m1 plus m2 plus m3, okay? And that is 81 divided by 12, and that is 6.75. Oh, actually, I made a mistake there. That is r squared that we just found, and then r, to find r, we take the square root of 81 over 12, which is about 2.6. Let me use my approximately 2.6, and that is centimeters. All right, so what did we just find there with the radius of gyration? All right, what that means is that if I have a total mass 1, mass 2, mass 3 of 12 grams, a total 12-gram mass, 2.6 centimeters away from my axis of rotation, that has the same inertia, moment of inertia, as this system with 3 different masses. So that's what that capital R is up there, that 2.6. So that you may not have even known what that meant a little while ago. That's what that means on there. This whole system in rotation has the same inertia as a single 12-gram mass placed 2.6 centimeters away from the axis of rotation. Okay, now we get to the calculus part of this section where we find the moment of inertia of a thin flat plate. So now we're not looking at individual masses located in specific points around the axis of rotation, but rather we have an area, but using calculus I can chop that area up into really thin rectangles. All right, that's where this comes in. Integrals come in useful, the ability to represent a whole area but look at specific individual sections and compute things about them, as we did with volume, as we did with the centroid in the last section. Okay, so we have, if a thin flat plate covering a region is bounded by some curves, y1 equals f1 of x, y2 equals f2 of x. We have bounds of our region, right? Those are the bounds of the integral. The moment of inertia of that plate with respect to the y-axis, so with y as the axis of rotation, is given by the sum of the moments of inertia of the individual elements. So when we're rotating around the y-axis, that is I sub y, we chop our region up into dx's, right? Because those vertical rectangles in the picture, those are all revolving around the y-axis for our moment of inertia. Okay, the mass of each element is given by K. K is the mass per unit area times y2 minus y1. That's the top minus the bottom, so the height of the rectangle. And y2 minus y1 dx is the area of the element. The distance of the element from the y-axis is x. Ultimately, this is our integral. I sub y, k times the integral from a to b, x squared. This is the height of the rectangle. That's the top minus the bottom curve, dx. If we are going with respect to the x-axis, so the x-axis is our axis of rotation, we chop our rectangles up dy. So the rectangles become horizontal when I'm revolving around the x-axis. And it's y squared, x2 minus x1, top minus bottom. Okay, so those are the big fancy formulas that we're going to use in a couple of examples. One additional note here is to find r, to find capital R, that is the radius of gyration. To find r, you divide by the mass, as we did in the last section, and then take the square root. And take the square root. Okay, so we get moment of inertia and radius of gyration. All right, let's take a look at this example. We have to find a moment of inertia and a radius of gyration, two things that we've been talking about here, for a plate covering the region bounded by this parabola, y equals 4x squared, x equals 1, and the x-axis, and here's the important part, tells me which formula to use, with respect to the y-axis. Okay, so that means our axis of rotation is the y-axis, and I am going to write down my I sub y formula, which is k times the integral from a to b of x squared, and then y2 minus y1 dx. The y's are plugging in my functions, top minus bottom. The k is the mass per unit area, and the x squared is that distance that each x value is away from the center, the axis of rotation. Okay, so it's plugging in what we know here. Let's see, they tell us that we're underneath this parabola. So inside of my parentheses, there's no top minus bottom, there's just a top. So 4x squared is in parentheses. Dx stays. X squared, that stays. That represents the distance away for each of my rectangular cross sections. Really, all I need to figure out are what are my bounds, right? We're revolving around the y-axis. as our axis of rotation, and they tell me from that I'm bounded by x equals 1. So this guy here is x equals 1. So the integral from 0 to 1, x squared times 4x squared dx. Awesome. So simplifying, integral from 0 to 1, let's see, 4x squared times x squared, we can simplify that, 4x to the 4th dx. Then take our antiderivative, 4/5 x to the 5th, keep my k out there, bounds are from 0 to 1, and we end up with, when you plug in your top bound minus bottom bound, 4k over 5. We still have a little bit more to go in this problem to find the radius of gyration. There's still a couple more steps here. So to find the radius of gyration, to find r, first we need the mass of the plate, and the mass of the plate, m, is equal to the integral from 0 to 1 of k, that's the mass per unit area. It's just a constant that we keep in the integral. Actually, I could keep that k out in front. Why don't I do that? K times the integral from 0 to 1 of just my function 4x squared dx. This is really just the formula above with that x squared, that distance taken out. And this kind of harkens back to what we did in the previous section also. So there should be some similarity there. There was just an x in the formula in the previous section, and then when you went on to the second step, you removed the x, or in the denominator of that fraction. Okay, so these topics are very similar in how you go through them, just kind of a slightly different formula each time. Okay, evaluating this integral, m is equal to k times, let's see, let me just get rid of my parentheses there, 4/3 x cubed, and that gets evaluated from 0 to 1. Okay, so we have k, actually let's go 4k over 3 when you plug in top bound minus bottom bound. All right, we're nearly done here. So we're almost at the point where we can write down what is the radius, that should be a capital R, the radius of gyration. So the radius of gyration in the y direction, this was I sub y, with I as my center of rotation, is equal to the 4k over 5 that we got in the first step. Actually, this is still squared, divided by 4k over 3. And when that all simplifies and all said and done, is 3/5. To find the radius of gyration, r sub y, take the square root of 3/5, and we could write that a couple of different ways, but I kind of just want to write it as radical 3/5. But if we did approximate it, let's write that down also, you would get 0.775, that is approximately. Okay, so what does that mean? Let me go back to my picture here, right? This whole plate exists over, from between 0 and 1. This thin plate is what we're calling it. If all of the mass here were located between, or were located at 0.775, so where would that be? If this is 1 right there, 0.775 might be right about there, 775. If all of the blue area, it's that dotted line, of course. If all of the blue area were condensed into that single strip, then it would have the same inertia as the whole blue triangular-ish plate itself. That's what that means. Okay, and we're going to stop there with this section. The text does go a little bit deeper into this topic, but I think that that's probably good, as much as I want to get into, at least. And I won't hold you accountable for anything that's more challenging than this type of a question. All right, so work on some of these homework questions. Ask questions if you struggle with them. It's, like I said, a little bit more complicated than some of the things that we were seeing in terms of understanding what you're doing. The actual evaluating the integral, use your calculator, but setting it up, that's the challenging part. So please let me know if you have questions. Thank you very much for watching. Have a wonderful day.